Questo sfondo, questo sfondo acustico, che cos'è?
Non viene da voi.
Dovrei capire da dove arriva.
Forse hai YouTube aperto?
Forse era la vecchia sessione di Dumushel, del talk di Dumushel che era passata.
Ha YouTube aperto adesso, prof?
No, adesso no.
Ok, non si sente niente. Okay.
Ma si sente, sì. Ok. Vediamo.
Okay, we are missing the first presenter and now also the last
Which
one.
means that actually we are missing 3 presenters.
Yes. I don't know if the person that is here with us, Robert.
Robert.
Don't know. Let's wait some minutes.
Hi, Robert is here.
Hi, Robert.
Hi.
You have a presentation today?
Yes. At 5 p.m.
Okay, so it's in the next session.
Is correct?
Robert is in the next session, not in this one.
Oh, no. Next.
Okay.
Thank you.
Yes.
Okay, maybe Mr. Morales is arrived. No.
We only have 3 participants besides us, so one of them is the last presenter. So I don't know. Maybe we can start the session and we can start with the last presenter, waiting for other presenters to come. But I'm not.
Why not? Why not? I agree.
Okay, thank you.
So I think this is the best option. At least we could also, another option could be to wait for another 3 minutes, but I don't know. I think that
maybe we can start and then we'll see if the other come.
So welcome to this session. In practice, this is a session from the general track of the conference, and should in practice we have potentially 4 papers, but we will see. And we are going to start from the last paper now, which is presented by Evgeny Romensky, with the title Computational Model for Compressible Two-Phase Flow in Deformed Porous Medium. So please, you can start. In the time, is 10 minutes plus 5 minutes for queries and answers.
Okay. Thank you very much. I will try to show my screen. Not easy. This one, okay. Just a moment. Can you see me?
We can see actually the screen, yes.
Okay, thank you very much. Good afternoon. Here in Novosibirsk evening, 5 hours difference. So I shall speak about a computational model for compressible multiphase flow in deformed porous medium. This is joint work with my colleagues from Novosibirsk, Galina Reshetova from University of Trento, Ilya Peshkov. Some information about this topic you can find in the following papers. So the next slide. A brief history of the issue for the description of wave processes in saturated porous media. People usually take the classical Beer approach, which was proposed more than 70 years ago, and it is a generally accepted model. Currently, there are a number of scientific and applied problems, such as hydraulic fracturing, extraction of geothermal energy, storage of carbon dioxide, and so on, which require the development of new models describing processes in porous media of complex rheology. And it is necessary to take into account finite deformations of the medium and its fracture. Our goal is to develop a new model of a deformable porous medium saturated with a mixture of compressible fluids, liquids, and gases. This model should take into account the finite elastoplastic deformation of the skeleton, and the governing differential equation of the model must be mathematically well posed, satisfy the laws of non-equilibrium thermodynamics, and allow the use of advanced numerical methods. All above properties of governing equation of the model ensure the reliability of the numerically obtained solutions. And one of the particular research goals is to develop a computational model for the propagation of small amplitude waves in a saturated porous medium. To develop the model, we use the symmetric hyperbolic thermodynamically compatible system theory, which provides the hyperbolicity of governing partial differential equations, in particular symmetric hyperbolicity in the sense of Friedrichs. Also, solutions must satisfy thermodynamic laws such as conservation of energy and growth of entropy. And equations, differential equations, should be Galilean invariant. I would like to know that many well-known equations of continuum mechanics and physics belong to this class, to the class of symmetric hyperbolic thermodynamically compatible systems. As an example, I can mention gas dynamic equation, magnetic hydrodynamics equations, equation of linear and nonlinear elasticity, superfluid helium, hydrodynamics equations, and so on. We propose a new symmetric hyperbolic thermodynamically compatible model of a saturated porous medium, which is based on the synthesis of the HTC unified model of continuum, which the description of which can be found in the following papers, and SHTC model of compressible multiphase flow, which also can be found in some papers. I briefly show the partial differential equations of the model, which is extension of the unified model. This model is a simple single entropy approximation. The partial differential equation consists of the set of conservation laws, total momentum conservation law, total mass conservation, conservation of each phase, equation for the relative velocity, balance equation of phase volume fractions, evolution of distortion, and entropy balance law. Each phase is characterized by its own parameters, volume fraction, mass fraction, mass density, velocity, and there is a set of mixed parameters. This is density, relative velocity, entropy, and distortion of the mixture, solid and fluid, of solid and fluid. Distortion is actually the inverse deformation gradient for elastic processes. So the important properties of this system is that it is hyperbolic and can be transformed to a symmetric hyperbolic system in the sense of Friedrich. Also, another important property is that the system admits an additional conservation law, energy conservation law, and entropy grows. So the solution to this system satisfies thermodynamics laws. To close this system, it is necessary to define the generalized internal energy E. We define it by the following way, and it's also necessary to define the source terms, which characterize the relaxation of phase pressure to a common value, relative velocity relaxation, and inelastic deformation. So this model is applicable to simulation of compressible inviscid or viscous multiphase flow in a deformed porous medium. So since our particular goal is to study small amplitude wave propagation in elastic porous medium saturated by a mixture of fluids, we can derive linearized equations. For example, on this slide you can see the governing equation for the small amplitude wave fields in an elastic porous medium saturated with a mixture of two fluids. This system is also hyperbolic and can be transformed to a symmetric hyperbolic system. And also the efficient finite difference scheme can be applied for numerical solution. I also would like to note that our model is applicable to the porous media for all range of porosity from 0 to 1. Here we see the reduced system for pure fluid on the left and for the pure solid. It is a nice property because we can do simulation for the porous media with inclusion of pure liquid and pure fluid by the single Pdpe system. We compared our model with the well-known Beer model. On the left slide, you see our equations. On the right, you see a Beer equation, and we show that the results obtained by our model and Beer model are very close. But the number of parameters in BIO model a little bit bigger. So on this slide, you see the comparison for the material constant shown in the table. Here you see a comparison, the dependence of fast and slow compressional wave on porosity. For moderate value of porosity, our results are close, but for porosity 0 and 1, our results gives a good agreement with expected physically, whereas the BIA model gives wrong results for slow compressional wave. On these pictures, you see a comparison of the dependence of the wave velocity on the frequency. You can see that the results are very close. So our model gives physically reasonable results. Okay, so we did a lot of, we solved a lot of numerical test problems. Here I show only few. Here you see the picture of wave propagation in the layered medium. Layers are fluid, porous medium, and pure elastic solid. Here we apply a diffuse interface approach, so we simulate regions with a pure fluid, pure solid, and porous medium. Here you can see all types of waves, including slow compressional waves. Here you see these waves. I just would like to know that the slow wave attenuates very fast, and it's not easy to see it, but on this picture you can see the slow compressional wave. Here you can see the result of the simulation of the wave propagation in a porous medium saturated with a viscous fluid. I just know that in our model, viscosity is modeled by hyperbolic approach. That means that we use a hyperbolic model for the viscous or flow, and which gives as a limiting case Navier-Stokes formulation for small shear relaxation time. The next slide is a wave field simulation in a medium saturated with a mixture of liquid and gas. Here it's interesting to study the dependence of the wave parameters on the ratio liquid and gas. Here you see some computation, and you can see that if the gas volume fraction increase, then the velocity of fast and slow compressional waves getting lower. And the amplitude of fast compressional wave increases, where the amplitude of slow compressional wave decreases. So actually we have a lot of simulation which can be found in the papers. And now conclusions and perspectives. So we propose a new symmetric hyperbolic thermodynamically compatible multi-phase model to simulate processes in a saturated porous medium. And the linearized version of the SHTC model is also hyperbolic. and it is applicable for modeling small amplitude wave fields. Our model predicts, as well as BIOS model, 3 types of waves: fast and slow compressional wave and a shear wave. The material parameters of our model are fully determined by the properties of the phases. We plan to continue our work, and it will include the extension of the model for more complex processes, such as flows of immiscible fluids with surface tension, phase transitions, destruction of skeleton, and so on. And application of this model, extension of the unified model, we would like to apply for analysis of flows in a digital core and at the pore scale in order to build a continuous porous medium model on mesoscale level, with the aim of further application to analysis of processes in a porous formation macro scale. Okay, thank you very much for your attention.
Thank you very much. Are there any questions from the audience?
Well, I could ask a question. Thanks for the presentation. So maybe this is a bit more general, but how sensitive are the parameters? Because there seems to be a lot of parameters in the system. So is it difficult to choose them correctly? Or?
Yes, okay. The main parameters such as sound velocities in liquid, gas, or elastic skeleton can be measured experimentally. So the only problem is to properly choose parameters in relaxation times, interfacial frictions, and so on. But it also can be done by a comparison with available experimental data. What about sensitive? They are not all, of course, some of them are sensitive, but the main problem is to feed the experiment, and it can be done.
Okay, thank you.
Many thanks. Other questions? Because apparently we have time. Any other question? No? So, okay, we can thank again the presenter and for his nice presentation. Apparently, we don't have we still don't have the first presenter.
Yes. So I think we can close this session, Raf.
Yes.
Because it's
so. I'm maybe we can.
We cannot anticipate the next one. Is too early.
Yes. I think I'm a bit disappointed because
I'm sorry.
because with a single no show, we're
ruining everything.
We had only one presentation in this session, so probably next time we should try to distribute the presentations from one single person among different sessions. Maybe it's a more robust solution.
Maybe it makes a sense to ask presenters to give their telephone numbers or something like else.
Yeah, maybe, yes. Yeah. Maybe, who knows, maybe Carlos Morales had a last time problem, who knows. Okay, so many thanks for your presentation, and actually, I wanted also to ask some questions, but it's not easy for me. But given that we have still a few minutes, I would like to ask about the computational procedure that at the end you have to adopt to solve that partial differential equation system that is originated from the formalization that you showed us. So, and especially in case of real applications. I mean, besides the academic examples, that typically are used as a benchmarks. No? In real life, you have strange boundary conditions, strange geometries, and in that case, you probably need more efficient computational techniques, and also even specific hardware to afford the solution of that problems. So, can you tell me something about this issue?
Okay, yes, you agree. We are doing now pure academic problems, of course. For a small amplitude wave simulation, we use finite difference scheme on staggered grids. It is very efficient scheme. It is people from geophysical community use it for the seismic simulations. So it's very efficient. Okay, but what concerns general nonlinear equations, we do it with our colleague from Renta, Mikhail Dumser. He is expert in numerical methods, and we usually explore discrete Galerkin method, high order accuracy, and so on. But of course, it's pure academic.
So actually, your solutions are analytic. You provided the analytic solutions of the formulation applied to those academic problems.
No, not.
No, it's numerical. It's numerical.
Numerical. It's everything is numerical because it's not easy to get an analytical solution. Of course.
Okay.
Equations are very complex. Yeah, we do numerically.
Very interesting. Okay, thank you very much again, and see you in the next section, hopefully, if you want to attend. The next section will start in about
45 minutes.
35? Okay.
45 at 15
45.
past 5.
Yes.
Okay. See you later.
Thank you very much. See you later. Thank you.
Bye.
Okay, see you.
See ya.
Bye.
tutto quello che penserò.
So, Professor Giorgio Massacci cannot do it.
Okay,
I think that we can start, Joe.
yes, good afternoon again. Welcome to this new session of the general track. We are still in the Jitsi room A. And okay, looking at the list of the participants, well, let's check. Is Vadim Petrov here among us? Who should be the first presenter? Vadim Petrov? Apparently not. Then, are you Vadim Petrov?
First, Petrov.
Are you the first presenter? Can you hear me?
Good.
Okay. Can you repeat your name, please?
Robert.
Robert. Oh, you are Robert. But Robert, the surname is. Apparently, you are the third presenter.
Ipanake. Robert
Okay.
Ipanake.
Oh, Robert Ipanake. Yes. Apparently, you are the third presenter. So I would like to check first if we have the first and second presenters, but I suspect that the answer is no. Okay. Is there anyone for the second paper?
I present two papers.
Two papers.
Yes.
Okay, so you are here for both, for the second and the third paper. Okay, so I'm going to introduce you for the first, which is the second paper. So you can start your presentation. Robert Ipanake presents the paper Some Properties of the Cross Product of Three Vectors in R4 with Mathematica. And you already know that you have 15 minutes, 10 of which should be presentation and 5 for query answers. So you can start.
Hi. You see my screen?
Yes? Absolutely.
Okay. Good afternoon for you. I start my presentation. The definition we used for this paper is this is We enunciated this lemma based on the definition. A properties corresponding to the cross product in R4. We prove these properties using the Mathematica Wolfram Mathematica. For example, here is the program we elaborate for complete the proof. Here we use a rule-based programming paradigm. This program are easy the proof. Then we enunciated this theorem. The proof is here. In this case, we not use it mathematics, but in the proof of this equality, we use it Mathematica. This equality is similar to Jacobi identity. This equality is very long, but with this program, we prove the equality. This is the program. In similar form, we enunciated two theorems and two corollaries. The demonstration is similarity with user Mathematica. This is my presentation. Excuse me, but my bad English.
Robert, can you hear me, Robert?
One question?
No, okay. No, I couldn't see anymore the shared screen. Are there any questions on this presentation about the results? Okay, apparently not. So I would like actually to ask, could you tell us something about the implications of these results? So are there any practical applications or in some field that can be maybe enhanced by the results that you achieved, that you showed us?
We make this work we propose it as is work with the surfaces in R4. We research about this item. Surfaces
Okay,
in
I understand, but no, this is quite clear. But I was just wondering whether maybe there are significant applications of these surfaces in R4, no? Because it would be interesting for our audience to know. So, can you list any application of this topic, this specific research field, research topic? Maybe in the next, maybe in the next paper, because apparently the next paper that you are going to present is quite related to this one, no? Apparently, yes. It is. So if there aren't other questions, I think it would be good to go ahead for the next presentation, which is being presented by Robert Ipanacque. The title is Parameterization of the clean battle by isometric transformations in R4 with Mathematica. So you can start this your presentation, Robert.
Okay. Okay. This is the second work, and I start my presentation. For show the geometrical interpretation, we use the projection from R4 to R3. For example, here the elements of set B, first, second, first, fourth, are the projections. The projections of I, J, K, L vectors in R4. Yeah, phi of P is the projection of any point from R4. For example, this is the parameterization of the cylinder. And the idea is easy. I show the process of construct the cylinder. In this case, I show the construction of Mapeos strut. The process It's easy. It's easy process. With this process, is easy to obtain it, to twisted Mobius strip and three twisted Mobius strip. Similarly, two-fold Mobius strip and three-fold Mobius strip. Now, the parameterization of the torus of revolution in R4. This process is the circumference in a plane around the other circumference in the plane xj. And this idea we use it for parameterization of the Klein model in R4. In this case, the circumference leaves the plane generated by n and k1. This is the graphical process, but the questions are in the paper. With this parameterization, we obtained the two Mobius strips in the this formed the Klein model. With this process, it's easy to obtain two twisted Klein model and three twisted Klein model. In general, any twisted Klein model, similarly to Klein model and three-fold Klein model, in general, any fold Klein model is these are the results of our investigation. Question?
Okay. Thank you very much, Robert. Are there any questions for this presentation? About this presentation? Any question? I have a short question, actually, Robert. Reading your abstract, you stated that the Klein bubble plays a crucial role in the main modern sciences. Could you try to explain to better explain this concept? For which type of in which type of applications is it relevant, or in which sciences, which fields is the Klein bottle playing a crucial role?
We start working in this topic basically is for now is teaching applications. Well, maybe in a future we, for example, for example, we are presented a paper about simulated construction antennas obtained from points in the torus. In this case, these antennas are planes. In this case, we in the future maybe construct antennas 3D. It's possible. It's possible, but slow. In the present, I don't know. In the present, no. But in future, it's possible.
I see. Okay, thank you very much, Robert. I think thank you very much for your presentations. Apparently, we still lack the first presenter, so I think we can move to the last presentation because I see that there is Fabio Di Fonso, who should be one of the authors of the last paper. So, hello. Fabio is going to present a paper entitled "On the Shooting Method Applied to Richards Equation with a Forcing Term." So you have plenty of time.
Yeah. All right. Good afternoon, everyone. So let me share my screen so I can. Okay. All right. So thank you for introducing me. Can you see my screen now? Okay.
No, we can see the screen. Yes.
Okay, great. Okay, so yes, I'm gonna talk about the shooting method applied to Richards equation with a forcing term, and so the general motivation of this study come from mainly agriculture and irrigation issues, but of course, when there are complex interactions between species with the water and the air and natural habitat, of course, it is necessary to have a model by which we can understand what's happening to the overall interactions. So, in particular, in this very involved scenarios, the water movement through unsaturated soils is crucial. It has quite important consequences on both species and environment. And for example, how we have to irrigate soils in order to have particular plants or cultivation grow up in a good way and optimal way, or how to deal with stormwater infiltration trench, how to manage landfills, or how to handle slope stability, and so on. So this kind of interaction are very important, and understanding water movement into soils is crucial for managing this phenomena. So what's the main tool? What's the main mathematical tool to understand and to simulate and to predict what can happen? So mainly the tool, the mathematical tool, is a Richards equation. Richards equation is a parabolic, highly nonlinear parabolic partial differential equation that in the 1D case relates the variation of the water quantity theta in time with its variation, of course, in space. And the dependence of the temporal derivative of theta with respect to the spatial derivative is highly nonlinear due to this term, these functions d and k. D is what we call the soil water diffusivity, and k is a hydraulic conductivity. These are very specific of the soil under consideration, and are let me say the many interesting parts in Richards equation because of their high nonlinearities. Now, in our approach, we have added a forcing term that could be seen either as a sink or as a source, and we call this R, as we can find very widespread in literature. And in our setting, R, the root water uptake stress function, will be just a function of the water content theta. While of course you can see in the literature, and you can of course easily think that it could also depend on the depth at which the water has arrived while infiltrating the soil, and on many other agronomic quantities. For example, root distribution into soils, root density into soils, porosity, and so on. Now, in our setting, we are just focusing on the dependence of R on the water quantity theta. And again, this is called the root water uptake, or also root water uptake model. Now, in this form, Richards equation could be written equivalently in three basically main forms. The theta form, that is what we see here, the so-called H or C form in terms of head pressure of water, or in a mixed form combining the first two. But of course, we will just consider the theta form here, both for simplicity and for what we will see later in terms of handling these very unpleasant nonlinear functions. Now, there is a relation between the diffusivity and the hydraulic conductivity, and this relation is just that the diffusivity is a multiple of the conductivity. It's just K times the derivative of the head pressure, also suction head, with respect to the water content theta. Okay, and this is just a relation, a mathematical relation between these two functions. But again, the hydraulic conductivity is specific of the soil under consideration. We will see that just changing soil, we will have different values for K. Essentially, these functions are nonlinear models that are determined by interpolating measurements again in a nonlinear fashion. And of course, we will have different models according to the way we interpolate these measures, these measurements. Okay, we have another assumption on the root water uptake term. Mainly, we just consider R positive or negative R negative. And also, and this is very classical in literature, these terms in zero, they are increasing and concave. So these are the two main assumptions that we do that we make on R, and these are very classical. I mean, you can find them almost everywhere in literature, and mostly for the commonly used models for the root water update. Okay, and this will come out to be very useful in what follows on the account of what we will be proving. Okay, so this is our setup. Again, we are dealing with a parabolic differential equation with a forcing term. Which kind of conditions do we put on this equation? So, as very common when you deal with a parabolic PDE, we handle this equation by Dirichlet boundary condition. So we are giving an initial condition at time t equals 0, theta 0 here. We give a top condition, theta sub 0, when z at z equals 0, level z equals 0, and a bottom condition, theta sub capital Z at the bottom. Of course, these are real measurement conditions. They come from measurements on the soil. And these are the usual conditions, Dirichlet boundary conditions, very useful in this context for solving Richard's equation. Of course, we can also consider different kind of initial condition. For example, Neumann conditions, when you just give initial condition like this theta super 0 and top conditions both on theta and on its gradient. This is also quite common, but it is not considered in this approach. Despite we will see that our approach will be very close to deal also with this kind of conditions. But we will see later when we'll apply shooting method to solve this problem. Now, what is our approach? First, so the idea is to resort to a classical transversal method of lines, what is called T-mol in literature, meaning that we first discretize the temporal operator, differential operator, and then we deal with the resulting equations in space. And then on the now, since Richard's equation again is a parabolic equation, once we have discretized the temporal differential operator, then we end up having a second order equation, and we will see later in details what I meant by this. And this is very prone to be dealt with with shooting method. Okay, so what we do first. Now, since we are very happy with the nonlinear functions, d, the diffusivity, and k, the conductivity, we resort to a very classical tool when dealing with parabolic equation. It's called Kirchhoff transform. So Kirchhoff transform is just the integral of the diffusivity function d, and we call this new variable mu. And now, once we rederive Richard's equation in terms of mu, we see that it just becomes the derivative of mu with respect to t times some a mass function equals as we can see here, a parabolic operator, it is called Kirchhoff operator, minus our root water uptake term. So this is quite nicer than the original equation because this looks like equation that we can deal with classical numerical methods. And okay, so we are quite happy because Kirchhoff transform has sensibly made Richard's equation easier to handle. All right, but we have to still choose. So of course we have to also transform our Dirichlet initial and boundary conditions in terms of this new variable mu. But we have to now decide which kind of model we're going to use to describe our soil. So in our setup, we have decided to use garden soil model. The reason is quite easy. Garden's model together with the Kirchhoff operator L makes Richard's equation a linear parabolic equation, because L, the Kirchhoff operator, is a linear elliptic differential operator. Okay, so this is very easy to see, and as we can see here, L is just a second-order derivative in space minus a multiple of the first-order derivative with respect to Z. So what we end up with? So we just discretize the time derivative with a first-order finite difference, and then we just express everything in terms of mu n. Of course, we will have dependence on the solution at previous time, but of course, when n is equal to 1, mu 0 is known since we are given an initial condition in time. So this is at least formally well posed. Everything is known at time 0, and then we can just think about how to integrate the Kirchhoff operator that now is a linear operator again. So just expressing and rearranging terms, we end up with, as I have anticipated at the beginning, with a second-order differential equation in mu n equals some vector field plus some forcing term, Rn. And again, in this case, according to the fact that we are, okay, so now the initial condition at time t equals 0 makes the right-hand side well posed. We know everything again for every n from 1 to capital N, and the boundary conditions at z equals 0 and z equals capital Z make our discretized second-order differential equation, that now is an ordinary differential equation, a boundary value problem. So we are given. So we have a second-order differential equation. We have an initial boundary condition, an initial condition in this case, as z equals 0, and a final condition as z equals capital Z. So we have two conditions. The order is 2. This is a boundary value problem. So that's why we came up with a shooting method, because we ask ourselves, okay, how can we deal with this second-order differential equation? Shooting method looks like being a natural choice for this equation, and that's what we did. So we resorted to shooting method. So of course we are supported by theoretical results that just assure us that that we're looking for a solution is a meaningful task. And so in general, if we are given a second-order differential equation, a boundary value problem, as long as we have that the derivative of our vector field f with respect to, in our case, mu, is positive, and the derivative of vector field with respect to the derivative of mu with respect to the integration variable is bounded, then we have, of course, in a compact interval, we have a existence and uniqueness of our solution. So in our case, we want to prove that these two conditions are fulfilled by our equation, by our model. Okay, so in our case, f, in terms of mu n and nu n is the derivative of mu with respect to z, is this function here, this vector field here, and the derivative of f with respect to mu n is the most complicated part we have to analyze, while the derivative of f with respect to nu n is just alpha. Now, this is required to be bounded according to the previous the theorem I've just showed you. And okay, second condition is satisfied, is fulfilled, and so we can focus on the first one. So in order for this to be positive, since our prime is assumed to be positive, we need this numerator here to be positive, and a sufficient condition for this to be positive is it is just that mu times capital F of mu is increasing. Okay, so if we are able to prove that this product here, this function is increasing, we're done. We have sufficient conditions that guarantee that our problem as a unique solution. Okay, now the result is quite easy, and I mean it is beautiful. Somehow it's very easy, and it can be proven that if f is a differentiable function over a compact interval I, and that is positive, decreasing, and convex, then this function is strictly increasing. Now we can prove this. We prove this in our paper by contradiction, but of course there could be many ways to prove this. And this works for us as a sufficient condition for the function mu times f of mu being increasing. Okay, so we are guaranteed that we can go on with the search of a solution, and we can apply shooting method, hoping that the numerical convergence works, since we know that the problem, the discretized problem, has a solution and it is unique. Okay, so how do we apply shooting method? Usually the general approach to solve boundary value problems is to recast them as a first order system of differential equations, and this is what we have done here. And in this, so in doing this, this becomes a first order differential equation that we could endow with initial conditions. Now, what's the caveat here is that we don't have actually an initial condition for nu n, because we are given a final condition for mu n. But now, here it comes a shooting method. So what's the idea of shooting method is to use a nonlinear zero finding routine, basically, to find the appropriate, the suitable value for this nu hat, this initial condition for nu, in order to satisfy the final condition on mu n. And this is very classical. So that's the idea. And so what's the algorithm that we have implemented both in Matlab and in Python, and the Python code is available on my GitHub page. So what we do first, we first discretize of course, we consider Richard's equation with the uptake. We apply a Kirchhoff transform to make it linear within Gardner constitutive relations. Then we discretize the temporal differential operator, and then we move on onto the first order system of ordinary differential equations that we have to integrate forward in time. And this is what we do. We just apply shooting method. So first we give a guess for nu at time 0, and then we apply a nonlinear solver to get the correct nu fulfilling the final condition on mu, and then we iterate until we have integrated our first order until z equals 0, z equal capital Z. And then we just keep going, because we have once we have integrated along the interval 0 capital Z, we have the solution at time tn, so we can move on the subsequent time. Okay, so let me just show you some specific examples on which we have applied our shooting method. I mean, the shooting method on Richard's equation, this transformed Richard's equation. So first example that I'm presenting is on a Lomi sand with this specific hydraulic parameters. So in this case, since we have considered a particular, it's called particular uptake term R, I mean, on the literature, everyone suggests to normalize quantities, and this is what we have done here. So in a very classical paper by Broadbridge and authors, they suggest this soil, and they propose this very specific root water uptake that is related to the diffusivity of the soil. Okay, so we have normalized the variables. We have considered the diffusivity and the root water uptake, which results from this choice as this constant C e to the mu, and R is R just follows from computations. We have given this top condition and this constant bottom condition. And then we can appreciate here the comparison between Pdpe of Matlab and our shooting method. So they're quite similar, despite, of course, our resolution is not as precise as Matlab. But I mean, the qualitative behavior of the two solutions is very similar, and we can see that this analogy also remains for a Silty Loam. A Silty Loam, where here we have changed something because we have considered a constant initial condition. A variable in depth initial condition, and boundary condition is constant at the top and at the bottom. But we have switched to a Fedez type stress function for the root water uptake term. That is essentially a piecewise, is a continuous function, but piecewise differentiable, because this is just a trapezoidal form if you just look at it, because here we have that this function is 0 and 1 outside the interval of absorption, and otherwise has these linear, these affine pieces connecting 0 and 1. So it's just a trapezoidal somehow. So it is continuous but not differentiable. Now the behavior again is very, very, very similar between Pdpe and the shooting, at least qualitatively speaking. One good point for us, for our method, is that it is robust with respect to this non-smooth behavior of all the functions involved in the Richards equation, in particular in this case the root water uptake term. So again, we have an analogy quite.
I think you should conclude.
Yeah. Okay. So in this third example, we have just the same soil as before, but with a different uptake function. It's called the Lee uptake function. And again, we have very similar behavior between Pdpe and the shooting method. But the most interesting one is that on a clay, we have that Matlab Pdpe with these initial conditions just blows up after 18 hours of numerical simulation, while our model is able to provide a meaningful result, physically meaningful. So giving us space to improve and to apply further this approach. So that's it. I'm sorry if it's too long. Okay, thank you for the attention.
Thank you, Fabio. Are there questions concerning this presentation, this last presentation? Any question? Apparently not, but actually I have some questions.
Yes.
Well, because I must say that indeed how roots affect soil hydraulic properties is actually very, very relevant, because for example, for planning landslide preventions, or even food, or even probably irrigation, I don't know, but it seems very relevant. I have a couple of questions, but first of all, in the last examples, I couldn't understand which parameters actually affect how the roots are actually modeled, because the roots, the sink term concerning the roots, I couldn't understand.
Yeah. Okay. As I said, we have in this last example, we have just considered the same uptake function as here, and here we have dependence on the potential transpiration, the maximal transpiration, and this is of course, as I said, this depends on the soil, and these are the transpiration.
Okay. So you this is quite clear now. So, but a more general question is, I was actually wondering, it is actually possible to apply the development approach through calibration on a real context? This is my question. I mean, using data from, I imagine, suitable sensors in a specific field site, no? So in other words, which type of difficulties you should address in order to apply in a real context? Is it possible to optimize the model? Which type of difficulties?
Okay. So, okay, I think that the answer is this model is very simple. I mean, apply shooting method is very simple, and even like discretization and application is very easy. One thing that we have not tried, and that is in our minds to pursue, is to like apply some data simulation techniques in order to like correct the prediction of the model with real data from measurements. This is something that it could be tried, and that could, of course, provide us some difficulties in applying such a method. And this is something that we have not tried, but we intend to. And actually, something that we are trying to apply this on is, as you were mentioning, some optimal control problem, and in particular, as you have correctly spotted, in particular, optimal irrigation. That is quite, it's very hot.
Yeah, that is an interesting, would be an interesting application. But so you are already thinking at a kind of data-driven version of
Actually, one of my co-authors, not for this paper, but on the paper that is the application of this one, because this is like the theoretical results, has already tried to have some like Kalman filter approach for data-driven
maybe also particle filtering. It could be also
example. That's very interesting.
Okay, thank you very much for your nice presentation. I would like also to thank also the other presenters and also the attendants, everyone, everybody, and so we will see hopefully tomorrow for the next sections.
Thank you.
Thank you very much. Bye.
Thank you, everybody. Bye-bye.
Thank you.
Thank you.
Thank you very much.
Andrea, mi sentite?
Sì.
Okay.
Okay.
Okay, we have to leave the room, please.
Yes.